Hi guys, and welcome back. Today I want to talk to you about an important phenomenon in physics known as beats. And we're not talking about like a drum beat or like Dr. Dre beats, but instead it has to do with the interference of two waves playing at the same time. So I'm going to demonstrate really quickly by way of using the guitar. And what I'm going to do is I'm going to play a harmonic on the guitar. So I want you to listen carefully to this tone. I'll do it again. Okay, now I'm going to play on a different string the same harmonic. One more time. Okay, so they're really close to the same thing, but they're not exactly the same. And I know that because if I play them both at the same time, I start to hear beats. I want you to listen carefully. I'm going to play them both, and I want you to listen. So here we go. So you should hear that fluttering up and down of the volume, which we call beats. Try again, listen. So that pulsing is what we call beats, and it has to do with two waves interfering both constructively and destructively with each other repeatedly over time and causing this beating sensation that we're hearing with our ears. So I want to talk about what makes it come about, how does it work, and kind of demonstrate why it happens. Okay, so this is an example of what we're talking about here, guys. So if we have two waves that are close to the same frequency, we can take a look at this graph here of the blue and the purplish wave. So one is a 50 hertz wave and the other one is a 60 hertz wave. So if they both start at the same time, at time 0, but they're not exactly the same frequency, then over time their peaks are going to start to not line up anymore and then line up again. So you can see here that for the 60 hertz wave, the peaks are a little bit closer together than they are for 50 hertz because you're getting 60 of these per second and only 50 of these per second. So after a certain amount of time, those peaks are no longer lining up. In fact, one is at a peak when the other one's at a trough. This sort of situation is what we call destructive interference. We have the crest of one wave and the trough of the other wave happening at the same time. Those two are going to have the effect of canceling each other out. So if they're both happening at the same time, that's going to cause the volume to be much, much more diminished than it was before. On the other hand, when you have a situation like this, later on the peaks line up again. This is called constructive interference. So when constructive interference happens, both waves are at the same point. They're both at a crest at the same time. So if that's happening, those two waves are going to add up. Instead of canceling each other out, they're going to add up and make a louder sound. So at 0.1 seconds in this graph, this is going to be a very loud sound. At 0.05 seconds, it's going to be a very soft sound. And then at 0.15, we're back to a soft sound again. So you have this beating. You have this situation where the volume is loud at one point and then quiet at another point, and it's oscillating back and forth between those two. If you look below that, this is summing the two graphs together. You'll notice that it's very tall in the beginning because they're both lined up. They're mostly lined up here. Then they're getting further out of phase, we call it here. And here they're completely out of phase, so we have very, very low volume. And then it repeats over and over again. So this is the phenomenon we know as beats. If you own or have used noise-canceling headphones before, noise-canceling headphones make use of the idea of destructive interference. So what they do is, not only do you have headphones, but you have a microphone built into those headphones. And that microphone picks up on ambient sounds outside. And basically what it will do is create another sound that sounds like the sound you're hearing outside, but completely out of phase with the sounds that it's picking up on the microphone. And when those two things are played simultaneously, you get destructive interference and it cancels out the noise. That's how they work. Okay, so to put this to bed and make sure we understand it one more time, here's what I've done. I've opened up Audacity, which is used for recording, and what I've done is I just introduced two different tracks into the mix, and they are pure tones. So this is going to be a single frequency sound. So what I'm going to do is I'm going to mute one of them and just play one and let you hear that. So take a listen. So this is a pure tone, single frequency sound. You can notice it's very continuous. Okay, now we're going to do the same thing with the other track. So I'm going to mute this track and I'm going to turn this one on instead. And I'm going to play it again. So you'll notice it sounds very similar. In fact, it almost sounds like exactly the same thing. In fact, it is slightly different. Okay, so not doing any tricks. All I'm going to do is unmute the first track so that both tracks play at the same time and let you listen to it one more time. So listen this time. So you can hear that pulsing in, out, in, out, in, out, in, out. That is the sensation of beats that we're talking about. So when we have two waves playing simultaneously that are slightly different frequencies, they're going to constructively and destructively interfere in time and give you that pulsing sensation we know as beats. So when musicians go to tune their instruments, they listen for those beats, and they're going to tune their instrument maybe by tightening or loosening the strings if it's a stringed instrument until they get rid of those beats. Then they know the two notes they're playing are exactly the same frequency. The interesting thing about beats is the faster the beating occurs, the more out of tune the two notes are. So the slower that happens, the closer they are to being exactly the same frequency. So that's it about beats. I hope you enjoyed that lesson, and I'll talk to you guys soon.